Okay, in this video I'm going to show you how to solve a mathematical integer problem for a telecommunication company that is given here as follows. We have we have n data flows that must be routed from a source S from a source S to a source T. And we have two possible links available for that, and they are characterized by their capacity. That is for link 1, U1 of 1 unit, and for the second link it's 2 units. So now the company that handles, so they are connections, and the company that handles the second link is 30% more expensive than the company handling the first link. And here in the table we have given now the demands that we have in our books, the required capacity in megabits per second, and the cost on link 1, and we know that for the second link it's 30% more expensive. So our task is now for first to formulate the mathematical program with the objective to minimize the routing costs for all the demands on the links. And the second part is how would we change now this model to the general situation where we include m possible links. So in order to formulate the mathematical problem, we need indices for our sets. For instance, we have here the list of demands, and we could give this list the index E that runs from 1 to n, for instance, and we call the set F, and that includes all our demands. Then we have given the required capacity that is used on by our demands. So we want to introduce the parameter A from E, so from our demands, and the demands are element of our set F. And we introduce a parameter name for our cost, C from E. We need is, of course, the name for the decision variable. Then we need also a factor how to denote the cost percentage difference of the links, and I call that P. And we have also given the capacity limits here in the text. So I call them, for the first case where we have just the two links, capacity limit U1 of link 1 and U2 of link 2. Okay, and I think this is as far as we need it. So it's always good in mathematical models to make a list. So this is our mathematical formulation. So we first denote our indices, and we have just one index E, that is the index for the set of demands, and the set, I called it F, that includes all demands from 1 to n. And then we have defined parameters. So our parameters just in our list are A from E, that is the capacity used by the demands, E, and just as an additional formulation. All for all demands E, they are element in the set F. Then we have the costs for routing. For the demands. So for the demand E. And then we have the cost percentage given from the cost percentage difference between the routing on link 1 and link 2. So this is the cost percentage difference between link 1 and link 2. And then we have our capacity limits of the links. So this is capacity of link 1, and this is capacity limit of link 2. What else? We need our decision variable. And we call that one. So the decision on the demands to route on link 1 is 1 if the demand or the package, so the demand E, is routed on link 1 and 0 otherwise. So here we have a binary decision variable, and the same for link 2 is 1 if the demand is routed on link 2 and 0 otherwise. Okay, so this is all that we need now to formulate our mathematical model. The mathematical model is now stated as follows. Our objective is to find the solution where we have minimized the routing costs for all our demands. So we minimize over all our demands, E from 1 to N, the overall costs, so CE multiplied by the selection for demand E on link 1. And now we have the cost percentage difference parameter P plus 1, and then multiplied by the costs CE for the decision variable for demand E on link 2. What else do we have? We have then some constraints. We have for one the constraint on the capacity for the links. So we say for all the demands E from 1 to N, the capacity usage for the demand E on link 1 in that case must be smaller or equal to the capacity of link 1. And on the other hand, the same is valid for the second link. All demands with their capacity usage shall be smaller or equal to the overall capacity of link 2. And then we have another constraint that gives now the selection of the arcs. So either link 1 or link 2 for the demand shall be selected. So it requires just to select one of the two of them. And this is valid for all our demands. Now let's look into how to change this model to regard M links despite just 2 of them. For that reasoning, we want now to generalize the model to regard M links. So we introduce a new index, J, that is the index for our sets of links. And now I give it a name. The set links is called L and includes the list of all links until link M. And what do we need to change in our parameters? Well, for instance, here we have the routing costs for all demand E, and we have given now the differences of the other links, or the cost of the other links with P. So now we give P an index over all our links and say this is now the cost percentage difference between link 1 and link J. And here also with respect to the capacity limits, we generalize now the U to denote links J until M. So this is now for all links that are element in the set L. The same is valid now for our decision variables. Now here we had 2 links and now we generalize it to regard links for demand E on link J. So this is for all demands that are in F and for all J that are element in the set L. Regarding now the mathematical model, let's see if I can get more space. We had regarded the minimization of routing costs for all our demands E, and now we also regard the set of links. So we reformulate it as being for all links from E to M over all demands from 1 to N. And now we regard just, or we generalize just the cost with respect to the cost differences. So we say P from J plus 1 is then the cost C from E multiplied by the decision variable X EJ. Regarding now our constraints, we generalize the constraint for the capacity limit as follows. So we say for all our demands from 1 to N, the capacity A from E multiplied by the decision variable must be smaller or equal to the overall capacity of that link. And that one is valid for all for all J that are element on our set L. And with respect to the second constraint, the selection of the links, we say for all links J from 1 to M, the selection of the link for the demand E must be just 1. And this is then valid also for all our demands E in F. Okay, let's look into how to implement this mathematical model into Excel and find a solution for it. So what I have done here, I transferred the table of our data that we had with respect to the demands and their capacities and the cost on the link 1 to Excel. So for our mathematical model, we need some more information. We need information on the cost on link 2. And we recall that this was expressed as a cost difference. I take that because it looks more nice. The cost difference from the cost of link 1 plus 30%. So we say the cost on link 1 plus 0.3, the 30%, multiplied by the cost of link 1. And this is then an error. Okay, the cost of link 2. Don't know why I complained, but now it's fine. And this we define for all the demands. Now the second thing that we need is the capacity limit on or of link 1, and that was 1. Try to make it look nice. And we have the capacity limit for link 2. That was given by 2. And now what we need is the decision variable. So we have we want to select those demands to run on either link 1 or link 2. So recall our mathematical model. The decision was given by XE for all the demands for link 1 or link 2. So I say here this is routing on link 1, and the other one is the routing on link 2. And this is now for, maybe that is a little awkward, this is now given for, let it be here, for all our demands. Now I give it a number. So this is the list of demand E, and this goes from 1 until 10. We have 10 demands given. And we want this now to be selected. So this is the selection or decision variables. I give them as yellow, maybe not screaming yellow, but this color is nice. So now we want to calculate the overall cost for the links. So we add a column that calculates this, and I use the color scheme to know where things are. So here we introduce the sum product to denote the sum of the links, the cost of the links multiplied by the decision variables. But then we want to limit the selection. So let's see if that has worked. Yes. Next thing, we want to define the total utilization of our links, because those the sum of the total demands being routed on link 1 shall not exceed the capacity limit of the link. So this is a sum of this is a sum product that regards the capacities of our demands multiplied by the decision variables to route the demand on link 1. We do now the same for the same for the second link. So we fix here in the formula the required capacity for the demands and check if that has worked. It did. And now we want to define our objective, and the objective is I denote it in blue. The objective now is to sum all the costs that we have calculated here in this column, to sum the overall cost of our selection. So that was what we just defined was the objective. Now we are in the problem where we regard just the two links. So we have minimized the total routing costs over these two links. We have defined for the utilization the limit, and we will give this calculation then over to the solver to be limited by the capacity limits of those links. And now we need to add the last constraint, so the decision to run demand E on link 1 and or to select link 2 for that shall be just 1. So we need to select where to route. So this is the selection constraint. And we say it should be either or. So we can say it's either this, the routing on link 1 or the routing on link 2. And this sum that we give then to the solver should be just 1. Okay, so the next thing is that we invoke the solver under data and solver. And now we give it the objective that is denoted in the minimization of the cost. So it's a minimization problem. Our changing variables are these two. The set. And we want, and this I put just next, we want them to be binary. Okay, so this we have given. Now the next thing that we need to add is the capacity utilization. So I give it one by one. The routing on link 1 shall not exceed the capacity limit of 1, and the same is valid for link 2. Then what else do we need? We need to add the constraint of the selection. So selecting for each demand just one link. So this should be equal to 1. And then do we need something else? Okay, so for the solver, this should be all that we need. Now we need to pay attention on the solution method that we select. So all our decision variables should be non-negative. And we want our problem to be solved by the simplex LP. We could set something like maximal time that we want the solver to calculate our problem instance. But the problem is small, so we don't need that. So let's see. Now we got a solution, and we can see now the selection of the links as follows. So we use for the routing on link 1, that is more cheap than the routing on link 2, the following demands. So we reach our capacity limit with the selection of those demands. And for link 2, we also use quite a lot of capacity, 1.7. So some of the packages need to be routed there, and we reach a total of 3,610 as objective in dollars. So if we want to extend now our model to consider multiple links, we can do it as follows. We can add another link or a dummy cell for Excel that is undefined for the moment, but let's add some just virtual costs. So this is, for instance, 20% more expensive than the cost on link 2, so this is the price difference. Just as an example. And then also for our decision variables, we need to extend our model now to regard also the routing on link N. And we need to extend our formula to regard also this dummy link. And the same is valid for the selection criteria that we add now here. And we would also need to regard the capacity limit of this link N. That would be given here. Let's just assume some data, but this of course you need to specify then. And we can just copy paste this formula over. Let's see if we were successful. Yes. And that is pretty much the extension in Excel to regard multiple links.